Today, our topic for this lecture is P and NP hard problem. Checking algorithm is something that allows us to verify whether or not the given problem solution is valid. So it doesn't necessarily solve the problem, but what it can do is take input to a problem and validate it. So C outputs yes if S represents a valid solution for one, and it will represent otherwise no. In the class NP, the checking should be efficient. That is, it should run in time polynomial. The various examples of NP are factorization, satisfiability, traveling salesman, vertex cover, independent set, etc. If we convert an optimization problem to a checking problem by providing a bound, we add only a log factor for binary search through solution space. Now the question arises, why this class is called NP? Well, NP is derived from non-deterministic polynomial time. The first and the third word, non-polynomial. From this, the letter comes N and P. That is, non-deterministically guess a solution, that is, magically deduce a solution, then in polynomial time verify the solution is correct or not. The origin of this concept is from computability theory, that is, non-deterministic Turing machine. You must have heard about them if you have ever read talk, but it is of no surprise if you haven't read, then also these problems are a part of computer science. The two classes people mainly talk about and which are confusing are P and NP. P is the class of problems with regular polynomial time algorithms. That is, the worst case complexity is in polynomial time. P is included in NP, and generate a solution and check it is P equal to NP. Intuitively, this should not be the case. A very important question which is confusing all is P not equal to NP? A more formal reason to believe this is many natural problems are in NP. Factorization, satisfiability, traveling salesman, vertex cover, independent set, and etc. are all in NP. These are all interreducible. The interreducible means that they are common. That is, if we get solution to one of the problem, then we can get the solution of others, like vertex cover and independent set. If we can solve one efficiently, we can solve them all. Now comes Boolean satisfiability. The Boolean variables are x, y, z, dot, dot, dot. Then the clauses, disjunction of literals. Here the literals in this are x, not y, and z. Then the formula is made up of conjunction of clauses, that is C and D and dot dot E. Here C, D, and E are clauses. The 3 set is a restricted form of set and has at most 3 literals. Now in this we will see reducing set to 3 set. Consider a 5 literal clause V or not W or X or not Y or Z. Now we will introduce a new literal A and split the above clause. Here we have split the clause like 3 literals in the right and 2 literals in the left with the help of A. So we have got that, which is represented in the third point. Now this formula is satisfiable if and only if original clause is. We will repeat this till all the clauses are of size 3 or less. If set is hard, so is 3 set, that is they are reducible. Now we are taking 3 set to independent set. That is, we are trying to reduce 3 set to independent set. Here we are going to construct a graph from a 3 set formula which is given in the next line. Here each clause is represented by a triangle, and every triangle's vertex is connected to every other triangle's respective vertex. That you can see that y is connected to not y, which is connected to y, which is connected to not y. Similarly, x and z are interconnected with all the triangles. Independent set picks one literal per clause to satisfy. For size of independent set equal to number of clauses. Now we are going to see reductions within NP. Set can be reduced to 3 set, and 3 set can be reduced to independent set. Similarly, independent set can be reduced to vertex cover. Reduction is transitive. You must have read about this in discrete mathematics. That is, if x is related to y and y is related to z, then x is related to z. And so is the case in this. So we can say that set is connected or reducible to vertex cover. Other interreducible NP problems are traveling salesman, integer linear programming, etc. The NP completeness by Cook-Levin theorem is a very interesting theorem and very famous theorem. Every problem in NP can be reduced to set. That is, original proof is by encoding commutations of Turing machines. Well, I have not given the original proof in this as it's too lengthy, and can replace by encoding of any generic computational model. Set is said to be complete for NP. It belongs to NP. Every problem in NP reduces to it. Since set is reduces to 3 set, and 3 set is also NP complete. So in general, to show P is NP complete, reduce some existing complete problem of NP to P. So we again come to the question, is P equal to or not equal to P? Well, a large class of practically useful problems are NP complete: scheduling, bin packing, optimal tools, etc. If one of them has a solution in P, all of them do, as they are interreducible by the transitive property. And many smart people have been working on these problems for centuries so that their achievements or discoveries can be used by the future generations. Empirical evidence that NP is different from P, but a formal proof is elusive and worth $1 million. So try your hands on, and thank you for the lecture.